Hi everyone, this is M.Revathi, Assistant Professor, Department of Computer Science, Artificial Intelligence and Data Science. Today we are going to discuss about the control loops and real-time system. First we see what is control loop. A control loop is a fundamental concept in automation and robotics that allows a system to monitor and adjust its behavior to reach a desired goal. It works by continuously measuring a process variables like speed, temperature, positions. So comparing it on set point and then using the difference, it's called the error. So to adjust the system's output, this concept applies to temperature control such as regulating the heat in a pot of water. A temperature sensor continuously monitors the water temperature, and if it too low, the system sends a signal to increase the heat. The controller uses this feedback to maintain the desired temperature, adjusting the heat supply as needed. This is also a closed loop system where constant feedback ensures that the system stays close to the desired state. Whether in robotics or heating system, closed loop control system use real-time feedback to monitor and correct processes, making them highly effective in achieving precise and consistent results. So here the diagram is to represent the temperature. So the temperature sensor is sent to the controller. Controller will send the signal to the wall. So it's check these are the example is the process the robot to takes an action, receives feedback and adjusts this. So in robotics and many other systems, control loops are fundamentals to ensuring tasks are performed correctly. A control loop works by continuously comparing the current state of the system with the desired state, adjusting the system action to minimize any discrepancy. For example, if a robot is instructed to move 12 inches forward, the system needs to monitor its progress and stop once the task is completed. A timer can serve as feedback to check how long the robot has been moving. And if the robot is moving at a rate of 3 inches per second, then loop would be ensure the robot moves 4 seconds, at which point the monitor is stopped. The closed loop system relies on feedback to adjust the robot actions and ensures it completes the task accurately. Next, we see the control loop control structure. A control loop control system operates by continuously monitoring the output of a process and making adjustment to maintain a desired state or set point. In such a system, sensors are used to measure the current outcome, such as temperature, speed, and or position. This sensor provides real-time data that reflects the actual conditions of the system. The controller receives this feedback and compares it to the desired set point, which represent the ideal or target value. If there is any discrepancy between the measured output and the set point, the control adjusts the system components such as valve, motor, or heating element to correct the error. So the adjustment ensures that the system self-corrects, bringing the output back in line with the desired value. The feedback loop creates a dynamic process where the system continuously adopts this charging, maintaining, and stability and pressures over time. This type of control system is widely used in various applications, including temperature regulation, speed control in robotics, and even modern heating and cooling systems. Next, we see the example. It's a robot docking. So a robot uses a camera to find LED on a docking station. It calculates the direction and distances. So the robot docking system relies on the proportional control mechanism, which is a part of the broader PID control system. In this setup, the robot uses a camera to locate LEDs on the clocking station, calculating both the direction and distance of the target. This information is used to generate an error signal which represents the difference between the robot's current position and the desired position at the docking station. The robot then adjusts its motor based on the error signal. The later the error, the stronger the correction needed This is the essence of proportional control, where the corrective action is directly proportional to the magnitude of the error. By adjusting its motor, the robot moves closer to the docking station, continuously recalculating the error and making finer adjustment as it gets near to the target. While this proportional method is effective in simpler application, it lacks the refinement of the full PID, which incorporate an integral and derivative term to address accumulated error and predict future changes respectively. So for basic docking task, proportional control provides a sufficient and efficient mean of alignment. So these are the example for robot docking. Next we see the real-time control. So real-time control involves executing the control loop consistently at fixed time interval. It's a reliable operation and timely responses in dynamic environment. So what is the soft real-time and hard real-time? What are the differences? So in soft real-time system, aim for timely execution but allow variability. So hard real-time system enforce strict timing guarantees. In robotics or aviation, hard real-time ensure that delays do not. So it's compromise safety or performance. So we come to the end of this section. I hope you enjoy this section. Thank you.